you. Thank you, Chimel and Andrea. This is thank you. And this is the first session of this workshop, which is on strange metals and topology. And we have 4 talks. The first one is Jie Shan from Cornell talking about topological quantum phase transitions in AB stacked MoTe2, WSe2, moiré bilayers. And I understand it's 25 minutes, roughly plus 5 minutes of question. Thank you, Jie. Floor is yours.
Okay. Well, thank you very much for the invitation and introduction. So today I'm just going to talk about, a couple of topological quantum phase transitions we observed in this moiré bilayer. So, this is something perhaps most people are familiar with, so if we overlay 2 monolayers of 2D materials with a small twist angle or small difference in lattice constant, moiré patterns can emerge, and you can get the new length scale on the order of 10 nanometer. So on the right, I'm showing you an SDM image of this moiré bilayer, which I'm going to talk about today. You can see individual atoms in this image. You can also see this new triangular moiré superlattice. And in this case, the twist angle is 0 or 180 degrees. So the period is on the order of 5 nanometer, and this is determined by the lattice mismatch between the 2 materials. It's on the order of 7%. So the moiré density is 5 times 10 to the 12 per centimeter square. Later, when I talk about doping density, mostly whole doping density, I'll use the moiré density as unit. So I'll say, filling equal to 1, that means, the whole density equals the moiré density. Okay, so this moiré pattern introduces periodical potential on the scale of the moiré period, and this introduces mini Brilliant zone, and the band now becomes folded, and the bottom becomes very flat. And this is a way to introduce a flat band in semiconductor moiré materials. If we have one isolated band, as I'm showing here for the top valence moiré band, Alan McDonough and his former student Fenchen Wu showed in 2018 that the low energy physics can be projected into the single band Hubbard model. There are 3 parameters in this model. One is the hopping matrix element T for 2 neighboring sites. In this case, it's on the order of 1 to 10 millielectron volts. On-site Coulomb repulsion energy is on the order of 100 millieV. And then the long-range Coulomb interaction, in this case, nearest the neighbor, is on the order of 50 millielectron volts. So in this case, if we just have a single isolated band, the bands are not topological. You have Chern number equals to 0. So in order to get a non-zero Chern number, we need to consider, at least 2 bands. And if you can intertwine those 2 bands by introducing, for example, complex hopping between the 2, you can get non-zero Chern number. In other words, introduce topological properties. Again, in this 2019 paper by the same authors, if, for example, one band with the one-year function concentrated at one high symmetry point of the triangular lattice, and the other band at a different high symmetry point of the triangular lattice, and together they form a honeycomb lattice, we can project this problem into the King-Malay model. So here, T is the hopping between the two different sites, which is complex. And then the spin orbit, actually in this case, is the interlayer, interband hopping here, T prime. And then we also have this potential difference between those two bands. So when Allen and Fenchen proposed this model, they considered twisted AA bilayer of moire. It turns out that we find this type of physics actually in very different system, in AB actually stacked heterobilayer between moire and a tungsten selenide, sorry. So in this case, the two bands actually are located in two different layers. So the moire lowest valence band is occupying one set of triangular lattice, and the tungsten actually occupy the B site of the honeycomb, the other set of triangular lattice. And now the sublattice potential is the same as interlayer potential. We can control interlayer potential very conveniently using displacement field. So in this case, if we apply just the outplane electrical field, you can invert the bands and induce valley contrasting non-zero Chern number, +1 or -1. So now let's consider the case when we have 2 holes per moire unit cell. So in other words, we have one band fully filled, and the Fermi level is between those two bands. So this is the case before band inversion. We should expect a band insulator, right? But once we invert the band, if we still keep the Fermi level between those two bands, then we expect something like a quantum spin Hall. So for quantum spin Hall, we have these two helical edge states, but time reversal symmetry is preserved. So there will be 0 charge Hall conductivity. But we do get the spin Hall conductivity quantized, but this is something difficult to measure. So in order to probe the state, we just look at the transport. And if transport is dominated by edge, you have a very good insulating bulk, then the resistance is h over 2e squared, because we have 2 conduction channels. So let's take a look at the experiment. So this is the experimental geometry. We have the heterobilayer. We have those 2 gates, which we can tune the doping density in the 2 layers, and also vary the displacement field. So in the following experiment, we're going to fix the doping density at 2 hole per moire unit cell, and vary the displacement field continuously. And this is work by postdoc Wenjing Zhao and grad student Kai-Fei Kang, and it's summarized in this archive paper. So first, let's take a look at the 4-point measurement. So we run current this way, and we measure the voltage drop here to get the longitudinal resistance. So before this critical electrical field, you can see that the resistance goes up as we cool down the sample. So this is a very typical insulating behavior. However, after this point, we see that resistance plateaus, and as we lower the temperature, resistance gets very close to this quantized value of h over 2e squared. It's not perfect, but within 85% of the quantized value. The bulk gap is somewhat small. In this case, we measure independently. It's on the order of 1 to 2 millielectron volts. So at this temperature, bulk still contributes a little bit. So to see the difference, we can run the current, measure the resistance differently. So for example, we can run current this way, and we ground those pins and measure the voltage drop, for example, across those 2 pins. And in that case, you short the edge channels, and now you see immediately, on the other side, the behavior is also like insulator. So, so this is a pretty reasonable evidence for quantum spin Hall. We've also done non-local transport measurements, which the result is consistent with this. Furthermore, for this particular band alignment, actually we can use out-of-plane magnetic field to induce actually a Chern insulator. So let me just explain how that works. So because those 2 layers are AB stacked, that means 180 degrees opposite. So at a K point, so the moire layer, if they spin down because of spin value locking in the K prime point or minus K point, the spin is up. For the tungsten layer, because of the AB stacking, the spin actually are opposite. So this is spin down, this is spin up. So now if we apply an outplane magnetic field, the Zeeman effect, at the K point and the minus K point actually are opposite. One will make the band gap smaller, the other will make band gap bigger at the other value. So now if we start with the case when are very close to band inversion, we have this helical edge states. So now you make one gap smaller, the other one is larger. So one is more negative, the other one becomes positive, right? So if equivalently, you are pushing one set of the helical edge states into the bulk. And eventually, at a larger B field, you kill one set of the edge state, and what's left will be this chiral edge state. And this is a Chern insulator. So let's take a look at an experiment. So this is the Hall resistance as a function of magnetic field. This is the longitudinal resistance as a function magnetic field. And the x-axis is the doping density. And the dashed lines actually are the Chern equal to C equal to 1 theoretical prediction. And you can see that the state agrees very well with Chern number equals to 1. We can take a look along this line. Then you can see that, the Hall resistance above about 1 Tesla sort of saturates to the quantized value close to, and then the longitudinal resistance correspondingly goes to something very small. We can also look at the temperature dependence at a fixed magnetic field, for example, 2 Tesla. When we decrease the temperature, the longitudinal resistance drops starting below about 3 Kelvin. So this tells us that the gap size is around about 3 Kelvin. And the Hall resistance approaches the quantized value below about 300 millikelvin. So this is all consistent with observation of a Chern insulating state. So let me just summarize what's happening at the filling equal to 2. we can apply an out-of-plane electrical field to induce band inversion. And once band inversion occurs, we can induce this topological phase transition from band insulator to quantum spin Hall insulator. And if you further apply an out-plane magnetic field, we can pretty much split the K-Malane into the Haldane model. Under a relatively small magnetic field around 1 Tesla, we can induce a Chern insulator. And in this case, this Chern insulator is valley polarized. Okay, so now I would like to switch gear and talk about what's happening if we just have doping density fixed at 1 hole per moiré unit cell. So before band inversion, we have half field band in the single particle picture. Because interaction is very strong, this actually is a MoTe insulator. So the band is split into lower and up Hubbard band. When we invert the band, you make the band topologically non-trivial. Then the question is, what could happen here? So the correlation could stabilize a Chern insulator or quantum anomalous Hall insulator. And indeed, this is what we observed experimentally. So on the left-hand side is the Hall resistance. On the right-hand side is the longitudinal resistance. So when we lower the temperature, you can see first magnetism kicks in. You see the hysteresis loop. And when we cool down more and more, this hysteresis loop becomes stronger. Below about 2.5 Kelvin, at 0 magnetic fields, the Hall resistance is quantized at h/e². At the same time, the longitudinal resistance goes to some small value. And if you can cool down even furthermore, in a newer measurement at a dilution temperature, this becomes vanishingly small. So, so this transport measurement says, indeed, there is a quantum anomalous Hall after band inversion. So the question is, what is the ground state of this quantum anomalous Hall state, and what is the mechanism, to induce this state? So, so first, we would like to probe or examine the charge distribution in this case. So initially, before band inversion, all the charges live in moly telluride layer. Tungsten layer is charge neutral. We can do optical measurements by looking at the excitonic resonance in tungsten selenide layer. So when it's charge neutral, we observe this very strong optical response due to neutral exciton. But when you increase the outer plane electrical field, some charge will be shifted, from one layer to the other layer. And optically, we can observe this charge exciton response. And this occurs, at this critical electrical field. And we can correlate, optical measurement with transport measurement. And this is exactly the critical field when quantum anomalous Hall effect emerges. So this measurement tells us that, upon charge transfer from one layer to the other, quantum anomalous Hall effect emerges. And what is the spin or valley alignment in this case? So this is a single particle picture I showed you earlier. So for AB stacked moly and the telluride, moly and the tungsten layer. So there is the spin valley locking. So when you switch from K to K prime, the spin switches. Also because we have AB stacking, so the spins are opposite in the two layers. So there could be two possible configurations. In one case, we can have hybridization of, for example, this band and this band. Then spins will have the same alignment. So this is a spin polarized case, right? And we can also have, hybridization between those two once you invert the band, and that will give us opposite spin alignment, but the valley will be polarized. So to test the configuration, the difference between this layer and that layer, we can, oh, by the way, I forgot to mention that all the mean field calculation actually predict, the valley polarized case should be the ground state. So we went ahead, tried to probe this, and the technique we use is, again, layer resolved magneto circular dichroism measurements. So let me just explain how we probe this. So in monolayer TMDs, actually, optical selection rules works for circularly polarized light. So we have a left and a right circularly polarized light exclusively coupled to either this configuration or that configuration. So you can think of the circular polarization, one-handedness is attached to one type of spin. And when both spin up and the spin down valence bands are not doped, then we have equal left and right circular polarized absorption. So in that case, magneto circular dichroism, which is the difference between the two, gives you 0, right? So now if we populate one of the bands, so in this case, for example, the spin up bands, and this will block the sigma plus transition. So in that case, you get non-zero magnetic circular dichroism with one sign. And we can look at the response in two different layers separately, because those two semiconductors have different exciton resonance energy, so we can layer resolve them. So if the spin alignment of the two layers are the same, then when we sweep the magnetic field, we expect the magnetic circular dichroism to change sign in the same way. So for example, from negative switch to positive. That's the spin polarized case. If it's valley polarized, that means spin anti-polarized. Then in that case, when we sweep with the magnetic field, in one layer, the MCD changes sign from negative to positive, but in the other layer, it changes from positive to negative. But eventually, when you apply large enough magnetic field, all spins will be polarized in the same direction. So they will all have the same sign at a large enough magnetic field. So this is our experimental result. We normalize the MCD, at a very large magnetic field, they saturate. So this black line is the RXY measurement. If you zoom in, you see hysteresis as the MCD showing here, this hysteresis. So when we sweep the magnetic field, MCD in both layers change sign from negative to positive here. So that just means, you know, it matches this description. So in the two layers, spin are co-polarized. That's what this measurement tells us. And you can also see that, you know, MCD does not saturate it immediately. It takes some field to saturate. This means that spins are canted. They are not icing-like. Okay, so I'm running out of time. So this result tells us that, you know, in the two layers, spin are co-polarized, maybe canted a little bit, but overall they align along the same direction. Therefore, they must come from different bands. So the spin up band from moly from the K valley and the spin up of tungsten from K prime valley, they have to, you know, the Fermi level cuts through them, and then the gap opens, right? So single particle gap is unlikely. So in order to achieve something like this, the K and the K prime valley most likely are coherent. So we think most likely we have a valley coherent state. And there is mechanism to account for something like this, you know, after we talk about our experimental results, you know, theorists already cook up a mechanism to explain this, mostly due to excitonic effect. I'm finishing, okay. So just to give you kind of a hand-waving picture of what's going on. So at a fixed filling one, you know, so we have all the charges living in the moly layer before the band inversion occurs. Then it's a charge transfer insulator. This is the lower Hubbard band. This is the upper Hubbard band. But the tungsten band is in between the lower and upper Hubbard band. And this delta is the charge transfer gap. But now if we transfer charge from one layer to the other, because of a very strong Coulomb interaction, the charge here actually is attached to the empty site left behind. And we can think about this as an exciton, right? So when the exciton binding energy exceeds the charge transfer gap, and that's something we control by this outer plane electric field, right? So when this condition is satisfied, we form excitons, and this the spontaneous exciton formation could explain, you know, the valley coherent Chern state we observed. So I would just like to put up my summary here, and you know, very importantly, you know, I would like to acknowledge my group who did this experiments, and also Professor Kim-Fan Mak, who co-supervised the group. We collaborate with Liang Fu's group at MIT on quantum anomalous Hall effect, Professor Tony Hines' group on the Intervalley coherent Chern optical measurements, and HBN is from the famous Japanese group. So I'll stop here.
Thank you very much, Jie. I'm just clapping for everybody for this very nice talk. If any questions, you can raise hands. And okay, Yang Zhi.
Hi, thank you for a very nice talk. My question is about the quantum spin hole part. Because so far you have not demonstrated the topological protection, namely when you, I would like to see how the edge state got destroyed by breaking time reversal symmetry. So I'm curious, have you done the in-plane magnetic field response experiment?
Yes, yes. we have some measurements on that. So the response for in-plane magnetic fields in this state and out of this state, the difference is huge. So, we look at the in-plane magnetic fields. So below this electrical field and above this electrical field, you see a huge difference. That's and large magneto resistance is observed over here.
Okay.
Yeah. But I understand, so the so let me put this way. I think so far all the different pieces point to they suggest that we likely have the quantum spin Hall, but of course, as you said, this is not something easy to verify, but all the different pieces are there and they all seem to agree, this is a quantum spin Hall insulator.
Okay, thank you.
Thank you, Koji.
Oh, hi, Jie. Yeah, beautiful
Hey.
talk. Beautiful talk. Yes, I'm just curious, for your quantum spin Hall data, what happens for magnetic field greater than 2 Tesla?
Oh, okay. Yeah,
so
so
the resistance actually come back up.
yeah, so so what's happening is the quantum Hall effect kicks in, so that just makes this complicated.
I see. So
Yeah.
you don't think this is more intrinsic to the system, or it's just the quantum Hall?
No, it's because under those magnetic fields, the lambda levels come in and
I see.
Yeah.
I see. You start to see lambda levels. Okay.
Yeah,
Okay.
yeah.
Yeah. Thank you. Thank you.
Thank you. Last question, Hanyu.
Hi, Jie. This is Sunny from Rice. Very exciting talk. I have a question regarding the correlation between the optical measurement and quantum spin Hall state, which you see yeah, that one, the previous slide. The polarons. So here, would you like to explain a little bit why polarons can form in this basically insulating state? And does it mean that the observation of polaron just purely optically could indicate some like very special electronic state by itself?
Okay, so I just want to clarify, so in the optics community, so what we have in mind of this is, we have electron hole pair in a sea of electrons, and that disturbs this electron sea. So this polaron so there are two branches, right? One is the repulsive, and the other one is attractive polaron, and that's something has been observed in monolayer, isolated monolayer of all the semiconductor TMDs, and it correlates well with doping into this material.
I see. So it purely says that there is carrier, and those carrier happens to be spin polarized.
No. So just from this optical measurements, we don't know whether they are polarized or not. We just know they're charge carriers, and they the electron hole sort of interact with this electron or hole C, and that gives you those, you can think of this like a charged excitons,
right?
And that's kind of the signature to tell you that the material is doped, you have some conduction electrons or conduction holes around, but we don't know about the spin of those. So this experiment just tells us that some charge already live in the tungsten layer.
Thank you.
Well, thank you very much, Jie. And there's one more question in the chat. If you could maybe just respond in the chat. Thank you so much for this really nice talk.
Is it possible to measure the band gap of quantum spin Hall states, maybe by temperature scaling? Yes, so we've done independent compressibility measurements. So you can see actually the answer is yes. I cannot go to that page. So, you know, before band inversion, the gap size is, you know, it decreases, right? So like a few milli electron volts. And then on the other side, after band inversion, it's relatively small. It's 1 to 2 milli electron volts. And you can also see that from the temperature dependence, as you said, you know, from the activation that's consistent.
Thank you. Thank you very much, Jie. Thank you again. It's a very nice result.